At 0342 hours on January 16, 1943, in the black freezing waters northeast of Cape Cod, the SS John P. Gaines cracked in half with the sound of 1,000 simultaneous rifle shots. The Liberty ship, laden with tanks, ammunition, and aviation fuel bound for Britain, simply broke apart amidships while steaming through moderate seas in 14-degree weather. Captain Harold Morrison, standing on the bridge wing during his watch change, heard the crack and felt the deck drop beneath his feet before the entire superstructure tilted violently to port. He had 17 minutes to get his crew off the ship before both halves sank. 38 men made it into lifeboats, but Chief Engineer Walter Kowalski and 2 oilers went down with the stern section, trapped in the engine room when the bulkheads collapsed. The John P. Gaines was the 7th Liberty ship to suffer catastrophic structural failure in 6 weeks, and the United States Maritime Commission had absolutely no idea why it kept happening. But thousands of miles away in the sprawling chaos of the Bethlehem Fairfield shipyard in Baltimore, Maryland, a third ship. The problem had started in December when the first reports of structural failures began filtering into the Maritime Commission's technical division in Washington. Liberty ships, those mass-produced cargo vessels being churned out every 6 weeks from shipyards across America, were breaking. Not from torpedo hits or storm damage or any kind of enemy action. They were just breaking, spontaneously, catastrophically, often in relatively calm seas. The SS Schenectady split completely in 2 while tied to the fitting-out dock in Portland, Oregon. On the same day, the John P. Gaines went down. The Schenectady hadn't even left port. She was just floating there, fully loaded with cargo, and suddenly there was a crack running from deck to keel. 2 halves of a brand new ship that had cost millions and thousands of man-hours to build. By the end of January, 19 Liberty ships had suffered serious hull cracks, and 7 had broken completely apart. The statistical projection was terrifying. If the failure rate continued, the Allies would lose more tonnage to structural collapse than to U-boats, and the entire He grabbed a ball-peen hammer from his tool belt and tapped the hull plate lightly, listening. The sound that came back was wrong. Not the solid ring of continuous steel, but something slightly hollow, slightly off. He tapped again, 6 inches to the left, and heard it again. By 1:30 in the morning, he'd tapped his way along 40 feet of hull plating on 3 different frames, and the sound was wrong everywhere he checked. His shift foreman, a former Navy boatswain's mate named Eddie Bronsky, thought Kowalczyk was losing his mind. "Stan, we got 11 ships to finish by March, and you're playing percussion on hole 408 at 1 in the goddamn morning," Bronsky said, standing in the scaffold with his clipboard and a thermos of coffee that had gone cold an hour ago. "What the hell are you hearing that 2,000 welders and a dozen inspectors missed?" Kowalczyk tried to explain. The steel plates they were welding into ship hulls were manufactured at tremendous temperatures and then allowed to cool. Standard process, nothing unusual. But when those plates were cut to specification with acetylene torches, they were heated again, locally, intensely, then welded, which meant more intense local heating, then allowed to cool in the freezing January air of Baltimore Harbor. The steel was experiencing massive thermal stress, expanding and contracting, and somewhere in that cycle microscopic cracks were forming, not big enough to see, not even big enough to fail inspection, but big enough to propagate under the cyclic loading of ocean waves. A Liberty ship hull flexes constantly at sea, riding swells, experiencing millions of tiny stress cycles. Those microscopic cracks were growing, spreading, until they reached critical length and the entire hull failed catastrophically. Vronsky stared at him. "Stan, you got a high school education, and you weld for a living. You really think you figured out something that MIT-educated naval architects missed?" Kowalczyk didn't argue. He just pointed at the hull plate and said, "Tap it yourself." Vronsky did grudgingly, and his expression changed. He heard it too. That subtle, wrong resonance that suggested the steel wasn't as solid as it appeared. By 3 in the morning, they'd woken up the night shift naval inspector, Lieutenant James Corrigan, who arrived with a portable ultrasonic testing device that had been developed for submarine hull inspection. Corrigan ran the transducer along the seams Kowalczyk had marked with chalk, and the oscilloscope readings confirmed it. Micro cracks, hundreds of them, running parallel to the weld lines just below the surface. Too deep for visual inspection, too shallow to show up on standard X-ray examination, but deep enough to fail catastrophically once the ship hit heavy weather and the hull began flexing. Hull 408 had been almost complete, representing over $1 million in construction costs and nearly 100,000 man-hours of labor. Corrigan immediately red-tagged the entire vessel and sent an emergency telegram to the Maritime Commission in Washington before dawn. The response came back that afternoon. All Liberty ship construction at Bethlehem Fairfield Shipyard was suspended pending investigation. 11 hulls under construction, nearly 9,000 workers sitting idle, tens of thousands of dollars in costs per day while the ships sat unfinished. The British were screaming for cargo capacity. The U-boats were sinking ships faster than America could replace them. And now one welder's observation had shut down an entire shipyard. Kowalczyk spent the next 3 days being interrogated by naval engineers, Maritime Commission investigators, and a team of metallurgists from Carnegie Mellon University who examined hull 408 with equipment that hadn't even existed when the war started. They confirmed everything. The micro cracks were real, they were widespread, and they were catastrophic. Statistical analysis suggested that between 40 and 60% of all Liberty ships constructed since October might have similar defects. That was potentially hundreds of ships, carrying hundreds of thousands of tons of cargo and tens of thousands of merchant mariners, all at risk of spontaneous structural failure. The economic impact alone was staggering. Hundreds of millions in ship construction costs, plus the incalculable cost of losing the war if the Atlantic supply line collapsed. But identifying the problem and solving the problem were two entirely different challenges. The metallurgists understood the physics. Steel contracts when cooled, and if the cooling happens too fast or too unevenly, internal stresses develop that create crack nucleation sites. But how do you prevent that in a production environment where speed is everything? The Liberty ship program was designed for mass production, not precision engineering. Henry Kaiser's shipyards were building complete ships in 6 weeks, using prefabricated sections and semi-skilled labor. Slowing down the welding process or adding stress relief heat treatment would add weeks to the construction schedule and cost millions. The Navy proposed scrapping all questionable hulls and starting over with improved procedures. The cost estimate for that solution was astronomical and would set the shipbuilding program back by 7 months. Britain couldn't wait 7 months. The strategic bomber offensive needed fuel and bombs delivered to English airfields now, not in the fall. General Eisenhower's North African campaign needed tanks and ammunition yesterday. Every day of delay meant more Allied soldiers dying because the supplies didn't arrive. Kowalczyk went back to work in early February, assigned to a special quality control team examining existing hulls for crack propagation. It was tedious, technical work involving ultrasonic testing and X-ray examination of weld seams. But Kowalczyk kept thinking about grain silos. Before the war, he'd spent 8 years welding agricultural storage structures across the Midwest, and grain silos had the same problem Liberty ships did. They experienced cyclic loading as grain was added and removed, and the steel walls had to flex without cracking. The solution grain silo builders used was simple: flexible gaskets at the joints, rubber or neoprene gaskets that allowed minimal movement without creating stress concentrations. Obviously, you couldn't put rubber gaskets in a ship's hull, but what if you could create a similar effect with the steel itself? What if the hull plates weren't rigidly welded together, but allowed just enough flex to dissipate stress without cracking? He tried explaining the concept to Lieutenant Corrigan one February afternoon, sketching on a scrap of paper with a carpenter's pencil while they sat in the shipyard cafeteria eating lunch. You put a gasket between the plates before welding, just a thin rubber gasket, maybe a 1/16 of an inch thick. It burns away when you weld over it, obviously, but it leaves a tiny gap, microscopic really, between the plate surfaces. That gap acts like a stress relief joint. The hull can flex minutely without building up internal stress. Corrigan looked at the sketch skeptically. "Stan, you're talking about deliberately introducing voids into the hull structure. That violates every principle of naval architecture. Ships need continuous structural integrity." Kowalczyk shook his head. "Not voids. Controlled discontinuities. Too small to weaken the structure, big enough to interrupt crack propagation, like expansion joints in a concrete sidewalk." The argument that followed involved 3 naval engineers, 2 metallurgists, and eventually a phone call to the Bureau of Ships in Washington. Nobody wanted to approve a modification based on the intuition of a welder who'd never taken a physics class. But the Liberty ship program was hemorrhaging credibility, and traditional solutions weren't working. The Maritime Commission authorized a test. Kowalczyk would modify one hull plate section on hull 412 using his gasket method, and they'd compare its stress characteristics to standard construction. The test would take nearly a week and cost thousands in labor and materials, and if it failed, Kowalczyk would be reassigned to less critical work. If it succeeded, they'd reconsider. Kowalczyk started work on February 15th at 6 in the morning. The rubber gaskets he'd requisitioned were industrial neoprene, a 1/16 of an inch thick, cut into strips 2 inches wide, and costing 12 cents per linear foot from a Baltimore industrial supplier. He laid the gasket strips between hull plates before tack welding, positioned so the welding arc would burn through the rubber but leave a microscopic gap in the joint. The process added less than a minute per linear foot of weld seam. His first test section on February 21st, mid-afternoon, Corrigan called Kowalczyk into the testing facility and showed him the results. 0 cracks. 0 measurable crack growth. The microscopic gaps created by burning away the rubber gaskets had interrupted every single crack nucleation site. The steel could flex under load without building up catastrophic internal stress. The modification worked, and it cost 12 cents per linear foot and added less than 1 minute per weld. By the end of February, the Maritime Commission had authorized immediate implementation across all Liberty ship construction. Kowalczyk's gasket method was installed on 14 ships under construction at Bethlehem Fairfield, then rolled out to 11 other shipyards by mid-March. The modification was retrofit into 53 existing Liberty ships that showed signs of crack formation. By the end of April, 67 ships had been modified using Kowalczyk's technique. Statistical tracking over the next 18 months showed that exactly 0 modified ships suffered catastrophic hull failure, while unmodified ships continued experiencing cracks at a rate of nearly 3%. The Navy's post-war analysis estimated that without the modification, between 60 and 90 Liberty ships would have suffered structural collapse, killing an estimated 8,400 merchant mariners and sinking war material valued at hundreds of millions of dollars. But on a freezing March night in 1943, just after 2 in the morning, Stanley Kowalczyk wasn't thinking about statistics or recognition or post-war analysis. He was standing on the deck of Hull 412, the first ship completely constructed using his modification, watching welders lay seams under portable floodlights in the bitter Baltimore cold. The ship would be christened SS James B. Weaver in less than 2 weeks and would make dozens of Atlantic crossings before being scrapped 20 years later. Kowalczyk lit a cigarette, his hands shaking from exhaustion and cold, and watched the welding arcs dance like fireflies across the hull. Somewhere out in the Atlantic, ships were breaking apart, killing men who'd volunteered to sail through U-boat-infested waters to keep Britain alive. But not this one. Not anymore. And then his foreman, Eddie Bronsky, appeared on the deck with an expression Kowalczyk had never seen before, urgent and pale even in the harsh sodium lights. "Stan, you need to come to the office, right now." The tone in Bronsky's voice meant something had gone catastrophically wrong, and as Kowalczyk followed him down 3 levels of scaffold and across the shipyard toward the administration building, he couldn't imagine what disaster had just... The office was freezing despite the coal stove burning in the corner, and the 3 men waiting inside looked like they'd been awake for days. Kowalczyk recognized 2 of them immediately. Commander Theodore Walsh from the Bureau of Ships, who'd flown in from Washington twice already to inspect the testing results, and Dr. Robert Hendricks from Carnegie Mellon, the metallurgist who'd confirmed the microcrack problem. The 3rd man was unfamiliar, older, wearing a civilian suit that looked expensive even under the harsh overhead light. He had the bearing of someone who was used to people standing when he entered a room. Walsh spoke first, his voice carefully neutral. "Kowalczyk, this is Mr. Henry Kaiser. He owns 6 Liberty shipyards on the West Coast and builds more of these vessels than anyone else in America." Kaiser stepped forward and extended his hand. His grip was firm, calloused, the hands of someone who'd done real work before becoming rich. "Mr. Kowalczyk, your modification works. We've confirmed it in Baltimore, and we've just received test results from Richmond Shipyard No. 2 in California, where we replicated your gasket method on 3 hulls. 0 crack propagation under cyclic loading. You've solved a problem that was about to shut down the entire emergency shipbuilding program." Kowalczyk nodded slowly, waiting for the other shoe to drop. Men like Kaiser didn't fly across the country in the middle of the night to deliver congratulations. "The problem," Kaiser continued, pulling out a chair and sitting down heavily, "is that we have 217 Liberty ships already at sea that were built before your modification, another 43 in the final stages of construction that can't be easily retrofit, and we've just received intelligence from the Office of Naval Intelligence that makes this situation considerably more complicated." He nodded to Commander Walsh, who opened a leather briefcase and pulled out a folder marked with red diagonal stripes. "Classified." Walsh cleared his throat. 10 days ago, a fishing trawler operating off the coast of Newfoundland recovered debris from what we've identified as the SS Richard Hovey, a Liberty ship that disappeared in January. We assumed U-boat attack, but the debris shows something different. He spread 3 photographs across the desk. Kowalczyk leaned forward, squinting in the dim light. The photos showed twisted metal, obviously from a ship's hull, but the fracture patterns were wrong for torpedo damage. Too clean, too linear. Walsh pointed to the largest piece. That's a catastrophic brittle fracture, identical to the failures we saw on the Schenectady and the John P. Gaines. The Richard Hovey didn't hit a mine or take a torpedo. She broke in half in the middle of the Atlantic, and she took 78 men with her. Dr. Hendricks spoke up, his voice quiet but urgent. We've been reviewing ship loss reports going back 6 months, cross-referencing with weather data and known U-boat positions. We now believe at least 11 Liberty ships attributed to enemy action were actually structural failures. That's over 800 merchant mariners dead from a manufacturing defect, not enemy fire. The room was silent, except for the hiss of the coal stove. Kowalczyk felt his stomach drop. 800 men. 800 men who died because of microscopic cracks in steel that he'd only figured out how to detect 3 weeks ago. Kaiser leaned forward, his expression grim. The Navy wants to recall every unmodified Liberty ship currently at sea for immediate inspection and retrofit. Do you understand what that means? We'd be pulling over 200 cargo vessels out of service simultaneously. The British have 47 days of food reserves remaining. 47 days. If we stop the convoys for even 2 weeks to retrofit ships, people in England start starving. And if we don't stop the convoys, more ships break apart and more men die. Kowalczyk's hands were shaking, and not from the cold. What do you need from me? Walsh pulled out another document, this one a typed technical specification with Kowalczyk's gasket modification described in dense engineering language he could barely follow. We need you to train retrofit teams, not here in Baltimore where you can supervise personally, but in Norfolk, Charleston, Mobile, Galveston, San Pedro, and Portland. 6 shipyards, 6 teams, all working simultaneously to modify ships as they come into port for routine resupply. The modifications have to be done in 72 hours or less per ship, because that's all the time we can afford to have them out of service. You'll have 2 weeks to train the first team in Norfolk, then move to the next yard. 6 cities in 6 weeks. We're asking you to teach hundreds of welders a technique you invented 3 weeks ago. And if any of them get it wrong, ships sink and men die. Kaiser stood up, pacing to the window that looked out over the shipyard where Hull 412 sat half-finished in the darkness. There's another problem. The Germans, if they figure out we have a structural weakness in our Liberty ships, they'll change tactics. Right now, U-boats try to sink ships with torpedoes, expensive torpedoes that they have limited quantities of. But if they know the ships are already prone to breaking apart, they just need to damage them enough to accelerate the crack propagation. A single deck gun round in the right location could split a Liberty ship in half. We've classified your modification as confidential. No public announcements, no technical papers, nothing that could leak to German intelligence. As far as the world knows, we're just doing routine maintenance upgrades. He turned back to Kowalczyk. You'll be traveling under a cover story as a quality control inspector. You'll be working night shifts to avoid attention, and you will not discuss the real nature of the modifications with anyone who doesn't have clearance. Is that clear? Kowalczyk looked at the 3 men staring at him, waiting for an answer. 3 weeks ago, he'd been a third-shift welder making 83 cents an hour. Now he was being asked to travel the country training retrofit teams to fix a problem that was killing men in the middle of the Atlantic Ocean. "When do I leave?" Walsh allowed himself a thin smile. "There's a train leaving Baltimore at 6:30 tomorrow morning. You'll be on it. A Navy liaison will meet you at Norfolk Naval Shipyard with the list of welders assigned to your training team. You'll have access to Hull 512, which is currently in dry dock for routine maintenance. That's your classroom. Teach them everything you know about detecting micro cracks and installing the gasket modification. 42 hours of training. Then they start working on active ships." He paused, then added quietly, "The first ship they'll retrofit is the SS William Clark. She's carrying aviation fuel and ammunition to Liverpool. Her hull was built in November, before we knew about the crack problem. If your training team does their job correctly, the William Clark makes it across the Atlantic. If they don't, she breaks apart somewhere between Cape Cod and Ireland, and 67 men die." The meeting ended at 03 or 7 hours. Kowalczyk walked back across the shipyard in darkness, past the hulking shadows of ships under construction, listening to the distant sound of pneumatic hammers and welding arcs. He'd have to go home, pack a bag, say goodbye to his wife Margaret without being able to explain where he was going or how long he'd be gone. She was 7 months pregnant with their first child, and now he was leaving for 6 weeks to travel the East Coast teaching welders how to save ships. He thought about the Richard Hovey, 78 men who drowned in the freezing Atlantic because steel cracked in ways no one had predicted. He thought about the William Clark, sitting in Norfolk right now, her hull laced with invisible fractures that would kill her crew unless his training was perfect. The weight of it was crushing. Norfolk Naval Shipyard, Virginia, March 4th, 1943. The training room was a converted storage warehouse with concrete floors, minimal heat, and 17 welders who looked at Kowalczyk with varying degrees of skepticism. They ranged in age from 19 to 56, a mix of experienced shipyard workers and recent recruits who'd been welding for less than 6 months. Kowalczyk had prepared a presentation, hand-drawn diagrams showing crack propagation patterns and stress concentration points. But looking at the faces staring back at him, he realized most of them didn't care about the theory. They wanted to know how to do the modification and get back to work. He ditched the diagrams and went straight to demonstration. "Steel is like people," he said, picking up a sample hull plate section that the Navy had prepared. "It remembers trauma. When you heat it up and cool it down fast, you're traumatizing the metal. The trauma creates scars, microscopic scars that you can't see, but they're there, and they grow every time the steel flexes." He grabbed his ball-peen hammer and tapped the plate. "Listen, that's what healthy steel sounds like." He tapped a second plate that had been deliberately thermal cycled to induce micro cracks. The sound was subtly different, slightly hollow. "That's steel with cracks. Your ears will learn the difference. It takes practice, but you'll learn." For the next 8 hours, he had them tap hull plates, learning to distinguish the acoustic signature of cracked steel. Some picked it up immediately, others struggled. A welder named Jimmy Patterson, 19 years old and fresh from a training program in Georgia, couldn't hear any difference at all. "It all sounds the same to me," Patterson admitted, frustrated and embarrassed. Kowalczyk pulled him aside during the break. "How's your vision?" Patterson shrugged. "Fine, I guess." Kowalczyk suspected otherwise and arranged for an eye exam. Turned out Patterson had significant hearing loss in his left ear from a childhood infection. He couldn't distinguish the subtle acoustic differences that crack detection required. It wasn't his fault, but it meant he couldn't do the inspection work. Kowalczyk reassigned him to gasket preparation, cutting the rubber strips to specification and organizing materials. It was unglamorous work, but critical. If the gaskets weren't cut correctly, the modification wouldn't work. Patterson approached it with meticulous attention to detail, measuring twice, cutting once, maintaining quality control that was better than half the experienced welders. The gasket installation training took another 16 hours. Kowalczyk demonstrated the technique on a practice hull section, showing them how to position the neoprene strips, how to tack weld without shifting the gasket, how to maintain consistent arc length so the rubber burned away completely without leaving residue. The gap needs to be between 0.03 and 0.05 inches, he explained. Too small, and it won't interrupt crack propagation. Too large, and you've weakened the structural integrity. The gasket burns away at exactly the right rate if you maintain proper arc length and travel speed. You'll practice until you can do this in your sleep, because some of you will be doing it on night shifts when you're exhausted. They practiced for hours, laying bead after bead on scrap plate sections, with Kowalczyk inspecting every weld under ultrasonic testing. The failure rate was initially 40%. Too fast, too slow, inconsistent arc length, poor tack weld placement. He made them do it again and again. By the end of the second day, the failure rate was down to 12%. On the morning of March 7th, the training team moved from the warehouse classroom to the SS William Clark, sitting in dry dock with her hull exposed for inspection. Kowalczyk divided them into 3 teams: inspection, gasket preparation, and welding. The inspection team, led by an experienced welder named Curtis Williams, who had perfect acoustic discrimination, would tap every frame from bow to stern, marking suspect areas with chalk. The preparation team would cut and position gaskets based on Williams' marks. The welding team would install the modification under Kowalczyk's direct supervision. They had 72 hours to complete the retrofit before the William Clark needed to rejoin convoy, ATX 239, assembling in Halifax. The clock started at over 800 hours. The first 6 hours were chaos. Williams' inspection team found crack indicators on 37% of the hull frames, far more than expected. That meant hundreds of linear feet of gasket installation, more than they'd planned for. The preparation team couldn't cut gaskets fast enough, creating a bottleneck. The welding team was moving too slowly, trying to maintain perfection when speed was equally critical. By mid-afternoon, they were 4 hours behind schedule. Kowalczyk called a halt and gathered everyone on the dock. "We're not going to make it at this pace. We need to work smarter. Williams, you're the best inspector, but you can't do it alone. Train 2 others to take sections of the hull. Patterson, you're cutting gaskets one at a time. Cut templates instead, then batch cut a dozen strips simultaneously. Welding team, you're doing beautiful work, but beautiful and slow means the William Clark misses her convoy and sits in port another week. We need good enough work done on time, not perfect work done late. Adjust." They adjusted. Williams trained 2 other welders in acoustic inspection, teaching them the specific sound signature to listen for. Patterson created cardboard templates for the most common gasket lengths and started batch cutting, quintupling his output. The welding team split into pairs, leapfrogging along the hull so one welder was always laying bead, while the other moved to the next position. By midnight, they were back on schedule. By dawn, on March 8th, they were 2 hours ahead. A foreman named Robert Lee Hutchins, 53 years old, with 30 years of shipyard experience, made his opinion clear during the first morning briefing. "Son, I was welding ships when you were in grade school. Now you're here telling me there's some magic rubber gasket that's going to save the Navy? Forgive me if I'm not convinced." Kowalczyk didn't argue. He just handed Hutchins a ball-peen hammer and pointed at 2 hull plate samples. "Tap them. Tell me which one has cracks." Hutchins tapped both plates, listened carefully, and his expression changed. "The one on the right." Kowalczyk nodded. "That's correct. Now tell me how you learned that in 30 years of shipyard work." Hutchins was silent for a moment, then said quietly, "I didn't." They worked well together after that. The Charleston team completed their first retrofit, the SS John Adams, in 64 hours. The Mobile team, trained the following week, did it in 59 hours. Galveston did it in 56. By the time Kowalczyk reached San Pedro, California, in early April, the process had been refined to 53 hours average. They attributed it to improved sonar, better air coverage, and increased destroyer production. They never knew that American cargo ships had simply stopped breaking apart on their own, eliminating nearly 12% of Allied shipping losses without firing a shot. The classification on Kowalczyk's modification wasn't lifted until June 1944, after D-Day, when the strategic situation had changed enough that the information was no longer critical. Even then, it was buried in a technical bulletin that few people read. Stanley Kowalczyk returned to Baltimore in late April 1943, exhausted, having traveled over 4,000 miles and trained 217 welders in 6 different cities. His wife Margaret had given birth to their daughter Sarah while he was in Galveston, and he'd missed it because he couldn't explain why he was traveling or when he'd return. He went back to 3rd shift at Bethlehem Fairfield Shipyard, welding hull plates on Liberty ships at 83 cents an hour. The Navy awarded him a civilian citation, classified, that he wasn't allowed to show anyone or discuss. Henry Kaiser sent him a personal letter and a $50 war bond, which seemed generous until Kowalczyk calculated that his modification had saved Kaiser's shipyards approximately $12 million in scrapped hulls and reconstruction costs. But on the night of May 3, 1943, standing on the deck of Hull 517 during his usual shift, Kowalczyk allowed himself a moment of satisfaction. Somewhere in the Atlantic, the SS William Clark was steaming toward Liverpool with a hull that wouldn't crack. The SS John Adams was carrying tanks to North Africa. The SS Thomas Jefferson was loaded with aviation fuel bound for England. 67 ships modified, tens of thousands of linear feet of gasket installation, hundreds of thousands of individual welds, 0 failures. He thought about the Richard Hovey, 78 men who died before anyone figured out what was killing them. He thought about Curtis Williams in Norfolk, now training his own teams. Jimmy Patterson in Galveston, cutting gaskets with meticulous precision despite his hearing loss. Robert Lee Hutchins in Charleston, who'd learned to tap hull plates and hear things he'd never heard in 30 years of shipyard work. The modification itself was absurdly simple. 12 cents of rubber per linear foot, less than a minute of additional labor per weld. The kind of solution that seems obvious in retrospect, but required one welder to connect grain silo construction techniques to Liberty ship failures in a way no naval architect had considered. Kowalczyk lit a cigarette and watched the welding arcs dance across Hull 517's framework. The war would continue for another 2 years. More ships would be built, more men would die, more battles would be won and lost. But the Liberty ships would keep sailing, carrying the cargo that kept Britain alive and supplied the invasions that would eventually defeat Germany. And they would keep sailing because a third-shift welder had learned to listen to the sound of cracked steel and had remembered how grain silos flex without breaking. In September 1945, after VJ Day, the Navy declassified most of the Liberty ship technical modifications. Kowalczyk's gasket method was published in the Journal of Naval Engineering with proper attribution. Several universities offered him teaching positions. Maritime insurance companies wanted to hire him as a consultant. He declined everything and stayed at Bethlehem Fairfield until the yard closed in 1950. Then he went back to welding water towers and grain silos across Pennsylvania and Ohio, the same work he'd done before the war. He died in 1981 at the age of 72, and his obituary in the Baltimore Sun mentioned that he'd worked in the shipyard during the war, but didn't specify what he'd done. The details were still technically classified, but every Liberty ship that survived the Atlantic crossing, every merchant mariner who made it home, every tank that reached North Africa, and every bomber that flew from English airfields owed a small debt to a welder who'd figured out that 12 cents of rubber could save a multi-million-dollar ship. The modification was eventually adopted as standard practice in naval construction worldwide, integrated into modern ship design without most people knowing where it came from. And somewhere in the archives of the United States Navy, there's still a classified folder with Kowalczyk's original hand-drawn sketches showing exactly how to install a gasket that burns away to leave a microscopic gap that saves lives. The file is labeled Solution to Emergency Shipbuilding Structural Failure Crisis, March 1943. The cover page has a single notation in pencil. Cost per ship, approximately $840. Lives saved, incalculable.